Okay, so today we're covering the mean value theorem. The mean value theorem. Okay, we've covered the intermediate value theorem about a month ago. Mean value theorem is another one of the theorems. We only have a few, but mean value theorem is kind of the key to calculus. If you want to know where you see calculus every day, it's the mean value theorem. Every day you guys see the mean value theorem. You just don't know about it. Okay, Jesseline, you ready? Okay. So if you rode in some sort of automobile here, car, bus, truck, whatever kind of, if you rode to school in some sort of automobile, this applies to you. Every time you ride in it, this applies to you. Okay. So what the mean value theorem says is, so if I'm looking from this point to this point here, so if I'm looking from this point here to this point here, right? So from 0 to, this is kind of 4.3, 4.4-ish, right? So if I'm looking from here to here, um, there's a line drawn. There's a line drawn, right? That line represents the average rate of change. The average rate of change. Okay. Rate of change is at one point. Instantaneous rate of change is at one point. This is the average rate of change here. Okay. This is the average rate of change. So obviously, so to find that, you would figure out what was your rise and what was your run. So I went over 4.4 or whatever, down about 1. That would be my rise over run, my average rate of change. What we've been doing with derivatives is average rate of change at one point. So at one point. So at this point here, the average rate of change looked like that. Okay? At one point. Instantaneous, we call it. Instantaneous. So when you look down on your car, when you're driving or in a car and you look down and it says 45 miles an hour at that means at that moment you're going 45 miles an hour. Now you're not going to go 45 miles an hour the whole way. You got to stop. There's traffic, there's stoplights, there's stop signs. You're going to eventually get to where you want to go, right? But that 45 miles an hour represents instantaneous. At that moment, that's how fast you're going. Okay? What average rate of change is overall? What was your average speed along the drive? Okay? So what it says is if you averaged a certain miles an hour, let's say from my house to here, I averaged 40 miles an hour, right? When I was on Herndon, I went a little faster. When I was in the country and there was no traffic, I went a little faster. But of course, I got to slow down for the stop signs. There's traffic. When you get to school, you got to slow down. So let's say I averaged 40. What the mean value theorem says is somewhere along the line from my house to this parking lot when I got here to school, I had to have gone 40 miles an hour at least once. I had to have looked down and um, my speedometer had to have said 40 miles an hour at least once. That's what the mean value theorem says. The mean value theorem says if your overall speed or your overall average rate of change is a number, somewhere along the line, you had to have been going that 40 miles an hour. Okay? That's what the average rate of, that's pretty much the mean value theorem right there. Okay? So if this right here, if this rate of change is, what do we say? It's -1/4-ish, right? -1/4-ish. You go down 1 and a little over 4, right? Somewhere along this path here, I had to have a slope of the same exact thing. If my overall rate of change was -1/4, somewhere along the path from black dot to black dot, I had to have a slope that matches that. Now, just by the eyeball test, where does it look like I would have a slope that would match that? Just the eyeball test. Where does it look like I would have a slope from black dot to black dot? Where does it look like I would have a slope of -1/4? Yeah, you rush. Around 2, yeah, I would say that's what I was thinking too. Around x equals 2, right? Around here, I kind of have a parallel. That's not too parallel, but somewhere around 2, right? Maybe right about there. Definitely around 2. Those lines, the green line and the red line I just drew, are parallel. That means they have the same rate of change. So that means around x equals 2, maybe 1.9, when x equals 1.9, I was going the same exact speed, right? Now, is there anywhere else that matches from dot to dot? Is there anywhere else that would match that same exact slope? Anywhere else that would have a tangent line that's parallel to that? Yes, no. I don't think so. There's nowhere else. Like here early on, I'm picking up speed, right? Here I'm picking up speed. So my slope is positive, right? And then I slow down, my slope is 0. And then here I'm decelerating, right? So that's what we're going to find. We're going to find where on here did I have the same slope? Where on here did I have the exact same slope as the average rate of change? So there's 2 things I got to find. First thing is, what was the average rate of change? What was the average? Got to find that first. And then I got to figure out where on my function does it have the derivative equal to that, which is pretty much what this says right here. This thing might look confusing, but it shouldn't be, because part of it looks familiar. What does that look like? What does that look like I'm doing? You guys have seen this many, many times, probably since 8th grade. You guys have seen it many, many, many times. What does that look like I'm doing here? Might not said f of a, but it said something close to that. What does that look like? Yeah, doesn't that look like y minus y1 over x2 minus, remember, you guys are used to seeing it like this. Y2 minus y1 over x2 minus x1, right? What is that? What we did that. Why did we do that? What were we trying to find? Slope, right? Yeah, we were trying to find slope. That's what this is. This is the average rate of change. The average rate of change, because slope is just a rate of change, right? So this part here, use a different color. Oops. This part here is the average rate of change from A to B, from beginning to end. From beginning to end. A is the start, B is the finish. Okay? So this guy right here is kind of the y2, this is kind of the y1, this is kind of the x2, and this is kind of the x1. That's what that kind of means. That's what that means. Okay? All right. So what does this guy mean? You've seen this in this class. What does that guy mean? Derivative. And what do I do with that derivative? What am I doing with that derivative? I'm finding the derivative, then doing what? Plugging in a number. Isn't C just a number? Finding the derivative and plugging in a number. Those are my steps right there, right? Those are the steps that I'm doing. Those are the 2 things I got to do. Okay. So it's not too bad. It's nothing we haven't done before. You guys have found slope many times. And found derivative and plugged in a number. You guys have done that many times in this class, right? So it's nothing you can't do. Okay, so conditions for using the mean value theorem. Okay, it has to be continuous over the interval. There has to be continuous. If it's not continuous at a certain number, then we can't use the mean value theorem. We just say mean value theorem does not apply because it's not continuous at whatever. Has to be differentiable too. Has to be differentiable. Okay, so it has to be differentiable means it has to have derivatives everywhere from beginning to end, right? This guy right here, from black dot to black dot, it was differentiable, right? I could find a derivative anywhere along this line from black dot to black dot. Nowhere is it going to be, there's no corners anywhere, right? There's no curves meeting at a point. And it's continuous because literally I don't have to pick up my pencil to go from dot to dot. Okay, that's what they mean. Okay. Okay, so let's look at the first problem. Okay. So apply the mean value theorem to the function over the interval. In each case, make sure the hypothesis is true. So make sure we can use it. Because if we can't use it, we got to say. Does not apply because it's not continuous. Does not apply because it's not differentiable. Okay. All right. If it is true, then find all the values of C inside the interval guaranteed by the mean value theorem. Okay, so that sounds a lot more complicated than it really is. Let me show you one more time what we're going to do. This is what we're going to do. Keep this in your head and it won't be that bad. This is what we're going to do. We're going to find the slope from dot to dot. What is the slope from dot to dot? We're going to figure that out, right? Rise over run. And then we're going to figure out C is the x value along this path that has the same slope, as the average rate of change. So the first thing we got to do is we have to find the average rate of change. Okay, that's the first thing. Average rate of change. Okay. Rate of change. Okay. How do we find the average rate of change? How do we find slope? They didn't give us a picture. We can't graph it because we can't use, this is a non-calculator question. So how do we find slope here? Right? The last problem I could just literally count. Rise over run, right? This one I can't though. So what do I do? There you go, right? Or even easier, since you guys are used to using this, change it to this. Y2 minus Y1 over X2 minus X1. Change it to that. If that makes more sense to you, it's the same thing we're doing. Okay? All right, so I need to find a Y1 and a Y2, first thing. And then I got to subtract them. How do I find Y1 and Y2? What does Y2 represent? What does Y1 represent? Or maybe it's easier to find the x's. Let's find the x's first. Do the x first. X2 and X1. What does X2 represent? What does X1 represent? Even easier than that. What does X1 and X2 represent? Yeah, those are going to be them, right? One of them is going to be -1 and one of them is going to be +1. So let's go back to our picture here. This is not the same function, but what does X1 and X2 represent? Yeah, the first dot, the starting dot, and the finishing dot, right? The very first dot and the very last dot, right? This is going to be A, comma, f of A, and B, comma, f of B. A fancy way of saying X and Y. This is X1, Y1, and this is X2, Y2, right? The 2 means the second dot, the 1 means the first dot. If it has a 1 by it, that means starting dot. If it has a 2 by it, that means finishing dot. So how do we fill in? Let's go here. So the x's, which one's going to go first, -1 or +1? The starting point or the finishing point? Finishing point. X2 is the finishing point. Good. So that's going to be 1. So that means -1 has to go over here. Good. Okay, so I got Y2 on top. That's the finishing point. How do I find the Y for the finishing point? The finishing point Y coordinate. I got the X coordinate, it's 1. How do I get the Y coordinate? There you go, plug it in. Plug it in. Plug in 1 to the function. So f of 1 equals 1 times 1 squared minus 1 minus 2. So we get 1 times 1 minus 1 minus 2. So that's 1 minus 2 times minus 2, which is -2. All right, that's Y2. Probably should use different colors. Okay. We're going to do the same thing to find Y1. So we get 1 times 1 squared minus 1 minus 2. Wait, why did I plug in 1? Nope, sorry, I'm going to plug in -1 down here. So I get -1 times 1 plus 1 minus 2. -1 times 0. So Y1 is 0. Okay. Now, the only thing left to do is to actually do the math. So I get -2 on top, and I get +2 on the bottom, which equals -1. That's the rate of change. That's the average rate of change from -1 to +1. Okay, let me label that average rate of change. Average rate of change. Okay, check. What do I do now? What do I do now? I got my average rate of change. What do I do now? Hmm? Yeah, so we want to look to see if it's, we haven't asked that question, right? Is it continuous or is it differentiable everywhere? So we definitely got to do that. So let's look at it. This, sometimes it's easier than not. So this guy right here, this guy is the function here, right? So it looks like if we wanted to graph it or whatever, we would do distributive property, right? We would do distributive property and then graph it, right? So it'd be x to the third minus x squared minus 2x, a cubic. Is there any numbers only between -1 and 1 that I can't plug in that I would get undefined for that guy? So if I plug in any numbers between here to this guy here, would I ever get something undefined? No. The answer is no. Why not? There's no division. Yeah. To get undefined, you have to have some sort of division and a 0 on the bottom. Well, there is no 0. It's just 1 on the bottom. Always will be 1, right? So we don't have to worry about continuity. And it's a regular cubic. There's no corners or anything. Cubics look like this. There's no corners or anything, especially with a little tight interval like -1, 1. That's very close together. So yeah, definitely check that. So good, we're there, we're good. So now we got to focus on this part right here. Because I found this part is done. Got that part. Now we got to focus on this part right here. What am I going to do that? How am I going to do that? Because I know to set it equal to each other, but how do I do that? What are my steps for that guy? Stop right there. That's all I got to do right there. Find the derivative. That's it. Isn't there a little tick mark here? I haven't done that yet. Right? Every single one of you should have said, oh, find the derivative. Who cares what this c is? I don't really care about that c right now. We haven't done this part yet, so we need to do that part. That's what we're going to do next. Okay? So let's find the derivative. To find f prime. So f prime, again, if I was going to find the derivative of this guy, I don't want to use product rule, especially when it's this kind of, it's this bad. It's to do something like that, it's x cubed minus x squared minus 2x. I'd rather use the power rule than have to use the quotient rule, or sorry, the product rule. So the derivative is going to be 3x squared minus 2x minus 2. Okay. So now let's go back. Let's go back to the very, very beginning. What did I say was the purpose of the mean value theorem? The purpose of the mean value theorem was to do what? What was I doing with this green line and the curve from dot to dot? What was I doing? Because the mean value theorem is very easy if you remember that. The steps are pretty easy if you just remember that. What was I trying to do with the green line and the curve? Yeah, as well? Exactly. That's it. So did I find this already? I found this already, right? The slope of this guy here? Check. Found that. So now I have to find where from dot to dot is it going to have the same exact slope? Where from dot to dot is it going to have the same slope? Why did I emphasize same? When you think of same in math, what should you be thinking? So we want to figure out where the slope, where the derivative is the same as the average rate of change. So what are we going to do? Where the derivative is the same as the average rate of change. What are we going to do? There you go. That's it. Set the derivative equal to the average rate of change. Where did I get -1? That was the slope, right? That was the average rate of change. And then solve for x, right? That's what the mean value theorem says. If you can remember that, where is the derivative and the average rate of change the same? That's what the mean value theorem says. Okay? So, first of all, it's a quadratic, so I got to get everything on the same side. So I'm going to add 1 to both sides. It's a quadratic, so I'm going to get 2 answers. So there's 2 ways to solve quadratics. One way is factoring, one way is quadratic formula. Quadratic formula always works, but it takes a little bit of time. So I always like to try factoring first. So if I factor this guy, first question I ask, is there a GCF? Is there a GCF between these 3 guys here? Something I can divide them all by. Nope. Okay, so factor now. So to factor, there's different ways. There's different little tricks teachers teach. I don't know how you guys learned, but this is the way a lot of teachers teach. A times C, A times C. A is the first term, the leading coefficient, which is 3. C is the constant, which is -1. And then B term in here. So what adds up to be -3 and divides, or adds up to be -2, but multiplies to be -3? Which 2 numbers? -3 and 1. There you go. So we're going to put a -3 and a -1 since those were our winners. One of them has to be a 3x and one of them has to be a regular x. Because I've got to make that 3 here. When I multiply, I've got to make that 3. So one of them has to be a 3x and one of them has to be just a regular x. So there's a couple tricks that you can do. One little trick that works is, I'll teach you the little trick, is to divide by a. If you divide these guys by a, it'll show you which one divides. So a was 3, so divide by a, and if it divides, divide it. So this guy divides by by 3, right? 3 divided by 3. This guy over here doesn't divide. It's just a fraction, right? This guy over here. So if it doesn't divide, you move the 3 up here, and that's the guy who gets the 3. Some teachers teach grouping, some teachers teach, it's just different ways to do that. But since it's not a factoring lesson, I'm just going to show you the quick way. Okay. So I get 2 answers. How do I find my 2 answers? That's right. Oh, yep. Thank you. This one's supposed to be a positive one. Yep. Because the positive one was over here, and I should have had a positive one over there. Yeah, so that means that's positive. Thank you. Yeah, otherwise our answers would have been wrong. Okay. How do I solve? Again, we're not in calculus territory now. We're not in calculus. We're in math 2, math 3 right now. Okay. Calculus we're done with. We finished calculus a while ago. Okay. So how do I figure out what my solutions are? Hmm? There you go, right? Most of you guys can probably do this in your head. So what would you get as answers when you do that? Negative 1/3. Because you got to subtract 1 and then divide. So negative 1/3. Okay? Those are the 2 points at which I would have the same exact slope as the average rate of change. Right? It would have the same exact slope. So which of those are my answers? Both of them, one of them, none of them? Which one are my C values? How do I know which ones? How do I know? How can I check? Hmm? There you go. If they're within the interval. So let's go back to the interval. The interval is from -1 to +1, right? Are both of those, or one of them, or none of them inside the interval? Both, yeah. One is on the edge of the interval, and because we have brackets here, you have brackets at 1, that means we can include 1. If there were parentheses here, 1 we would not count. Okay, but because there's brackets, that means they want us to include 1. So both of these are the answer. Okay. Okay, so before we go on, another reason why mean value theorem is so important is because you see it all the time. Especially you guys. You guys are young drivers. You guys will see this all the time. Have you ever heard of the term speed trap? A speed trap that police will set up? You guys heard of speed traps? Well, there's different kinds of speed traps. One speed trap is where they use the mean value theorem. This is what they'll do. You're driving down the highway. Usually they do this on highways. So they're driving down the highway and you see a cop and he's not pulling people over, but he's just watching. So what they do is they time you. So they say, okay, this guy, okay, so they came by me at 8:05. A couple miles down the road, 5, 10 miles down the road, they have another cop and they're clocking to see when this car pulls by. If this car pulls by before a certain time, they know using the mean value theorem that your average rate of speed, because a lot of people have like radar detectors, so they know when cops are coming, right? Well, they slow down when they pass the cop, but then when they're past the cop, they speed up again, and then they slow down when they see the cop. So when they're passing the cop, they're going the speed limit. But in between there, because they got from point A to point B so fast, the cops can deduce that somewhere along the line they were going over the speed limit because their average speed from point A to point B was 80 miles an hour. I don't care that you're going 65 by me. Somewhere along the line, calculus said you had to have been going 80 miles an hour. It didn't matter that I didn't see you. There's no way physics and calculus, that's how physics and calculus work. You had to have been going over the speed limit, which is 70. I can give you a ticket. That's a speed trap. So that's one way that it's a legitimate way that people get speeding tickets. They won't clock you, right? It's a way for them to get around the people have the radars, right? Because that's how they use it. They use it using calculus because they said from point A to point B, you average 80 miles an hour to get from point A to point B 5 miles down the road. Somewhere along the line, you had to have been going 80 miles an hour, which is against the law. Here's your ticket. That's what that's one type of speed trap. There's other types of speed traps too, but that's one time. And it doesn't matter that they didn't see you going 80 miles an hour. Calculus and physics tell you they had to have been going 80 miles an hour to get there that fast. Right? So you got to be careful on the road because like I said, that's another way you see it. Usually on the highway, when people stay on the highway for a while, it's not really on the street because people turn off on the street and stuff like that. But when you're on the highway, like long stretches of highway, that's usually where they'll catch you. A lot of times you'll see signs on the road saying they're doing that. They'll have signs on the road saying that you're like, okay, whatever. That you don't even know what that is. Most people don't even know what that is. But if you look on signs on the road, they'll say, or monitoring you by airplane for speeds or whatever, that's what they're doing. Okay, that's what they're doing. They're catching people using those kind of methods. But when you see the science, you're like, whatever, you know. But it is a legitimate way they do it. It's called a speed track. Okay, they use the mean value theorem to do that. So that's what I always tell people. This is pertinent, very pertinent to drivers everywhere. Okay, so you got to be careful. Even if there's no cops on the road, you got to be careful. Okay, so here we go. This is the graph of what we just graphed. This is the one that we just graphed here. I want to show you how it applies. I want to show you. So our average rate of change from 1 to -1. So from -1 to +1. So at -1, we had this dot here. -1, it was this dot here, right? And at +1, we're right here, right? And we found that the average rate of change here, right, was -1, right? In between there, so in between from black dot to black dot, what we found is 2 places where it would have the same exact average rate of change. The first one we found was -1/3. -1/3 is probably right about there. Maybe a little higher, right about there. Parallel, right? Right there. And the other one we found was +1, the very end. The very end. Okay? That's how it applies there. That's where it tells us. It'll tell us where we have the same exact slope. The same exact slope. Okay? They won't always give you a picture. Sometimes they do, sometimes they don't. I just wanted to give you the visual there. Okay? Okay, so let's look at the next one. I want you to try this one. Give this one a shot. Read the question, go over it, look at it, analyze it, and then go for it. Alda? Did you go on? Were you able to go on? Okay. Mean value theorem on this one does not apply because f of x is not continuous at x equals +1, right? If I plug in 1 to the original, I would get 0 on the bottom. That's the definition of a, it'd be an asymptote there, right? It'd be an asymptote if I graphed it. And because 1 is in the interval, can't apply it. Can't apply it, right? That's the thing. If you do this problem without knowing that, you'll get an answer. But that answer won't be correct because it doesn't apply. You got to check. So let's say I change this problem. This is what I do sometimes. Let's say I change this problem and I make it from 2 to 5. Same f of x. Would this still be an issue? No, because 1 is not in the interval. 1 is outside the interval. So I could change that to 2 to 5, and you could do the problem just like you would. You probably would have got the same answer you guys did earlier, right? So you got to be careful by checking that. Okay, guys? You got to be careful when you're doing this because First thing you should always do is look at it and say, okay, is there anywhere where it's not going to be continuous? And if your answer is yes, find out if it's in the interval. If it is, stop right there and say does not apply. Okay? Or if it's something like this, right? The one we just did earlier, this guy doesn't even have a fraction. There's no way to make this undefined, right? So then keep going. Don't worry about it. Keep going. Okay? All right, so we're going to finish these notes on Monday, and then I'll give you a chance to start on the assignment on Monday. I'm not going to assign anything new over the weekend. The only assignment that is still out there, still active, is the one we started yesterday. Okay, that one's due on Monday by the end of the day. Okay? So there's nothing new assigned today. We'll finish these on Monday.